Today, we're stepping straight into the microscopic world of particle physics for what I can really only describe as a high-stakes missing persons case. Well, actually, scratch that. It's a missing particles case. At the recent Large Hadron Collider physics conference, the brilliant minds at the Atlas collaboration dropped this absolutely fascinating new report. They finally tracked down a highly elusive, incredibly tiny suspect that has been entirely evading detection for a while now. So we're going to put on our quantum detective hats and look at exactly how they cracked this case. Okay, let's dive right into this. 82, that is the prolific number of brand new particles discovered at CERN's Large Hadron Collider. I mean, it's just a staggering achievement. The Large Hadron Collider is essentially the world's largest, most powerful microscope, and it's been systematically filling in the blank spots of our universe's family tree. But out of all those 82 discoveries, the newest addition to the roster is particularly special, mostly because of just how ridiculously hard it was to find. Let's move into the first phase of our investigation with Section 1, Meet the New Particle, the B star plus Meson. Now, our suspect is a meson. That just means it's a composite particle. Specifically, it's formed by binding together just two fundamental blocks, a charm quark and a bottom antiquark. That's the whole shebang. Just those two heavy fundamental blocks bound really tightly together. But here is where the plot thickens a bit. See, we already knew about the standard version of this particle, the BC plus meson. What the Atlas team discovered is its newly found excited counterpart, the BC star plus meson. Notice that little asterisk? That indicates this particle is excited. Both particles consist of the exact same building blocks, that charm quark and bottom antiquark, but the excited version exists in a completely different, highly energetic state. It's kind of like looking at the exact same person, right? But one is completely relaxed on the couch, and the other just chugged 3 espressos and is practically vibrating with energy.
So why do we even care about an over-caffeinated meson? That brings us to Section 2, the strong force, a fundamental mystery.
The CERN report leaves the motive out pretty clearly. Despite decades of intense study, the strong nuclear force, the fundamental force that glues quarks together to form basically all the matter in our universe, it still has a lot of poorly understood secrets. So studying a system like the BC plus family, that is like hitting the jackpot for physicists. Because there is such a massive weight difference between the charm quark and the bottom antiquark, it creates this highly unique, really extreme environment. It gives researchers an absolutely unparalleled laboratory to watch the strong force flex its muscles and really test our theoretical models of how the universe is held together. Of course, wanting to find a particle and actually finding it are two very different things. Let's look at Section 3, the smoking gun, and our microscopic challenge. So, the crucial point here is that the complication lies in its instability. When the excited BC plus meson is created, it is incredibly unstable. It desperately wants to relax back down into that standard BC plus state, and to do that, it sheds its extra energy by shooting off a photon, a particle of light. Successfully proving the excited meson was there means scientists absolutely have to catch that specific photon in the act. That photon? That's our smoking gun. Without it, there's literally no proof the excited particle ever existed in the first place. Let's break down the forensic timeline of how this actually plays out inside the collider. First, boom, we have a massive, high-energy proton-proton collision. In the chaotic aftermath of that crash, our excited suspect is born. Second, almost instantly, it rapidly decays, relaxing into the standard BC plus meson and spitting out that vital photon. And third, that photon travels outward and converts to an electron-positron pair. As you can imagine, this is an incredibly fast, highly complex chain of microscopic events. And here is exactly why that smoking gun photon has been so famously elusive. Because the mass difference between the excited state and the relaxed state is incredibly tiny, the photon that gets emitted carries almost zero energy. I mean, it is remarkably weak. Searching for this specific low-energy photon inside the chaotic, roaring environment of the Large Hadron Collider, it's literally like trying to hear a single whisper in the middle of a Category 5 hurricane. It just effortlessly slips right past all our normal detection methods. But hey, you don't build the most complex machine in human history without a few brilliant workarounds, right? That brings us to Section 4, detection trick, and the ingenious forensics used to crack the case. Since the standard methods for identifying photons were completely blind to something with this little energy, the Atlas team had to change tactics. Instead of looking for the photon directly, they decided to look for its footprints. They scoured the Atlas tracking detector for those electron-positron pairs we talked about earlier. By finding closely spaced charged particle tracks, they could essentially play the tape in reverse. They traced these tracks backwards to a displaced common point, meaning a tiny, tiny spot just slightly away from the main proton crash site. To actually pull this off, they had to deploy a completely dedicated, highly specialized track reconstruction procedure designed just for this incredibly delicate task. Now, what's really interesting about this is just how delicate that task was. The tracking detector was picking up transverse momentum as low as 100 MeV. To put that into perspective for a second, that is significantly lower than the energy levels typically studied in standard Atlas analyses. They basically had to tune their instruments to be sensitive to the absolute faintest of signals, pushing the tracking detector to incredible limits just to reconstruct those elusive photons. Let's see how this all builds up. By successfully tracking those tiny whispers of energy, the Atlas team confidently identified the BC plus meson and actually measured the mass difference. The final verdict? 64.5, give or take 1.4 MeV. The forensic precision here is it's stunning. They successfully captured and measured a microscopic whisper. Case closed, right? The suspect has been found and weighed. But, as always in physics, a closed case is usually just Section 5, what this means next, and the opening chapter of a much bigger story. And this brilliantly illustrates why particle physics is so vital for us. This isn't just about adding a new name to a textbook somewhere. This exact measurement of 64.5 MeV provides completely new, critical data for the theoretical models that describe how heavy quarks operate. While the measurement lines up nicely with available theoretical expectations, the report notes it slightly deviates from the absolute newest high-precision calculations. And you know what? That deviation is incredibly exciting. It means we now have the hard data needed to tweak and improve those models, bringing us one giant step closer to fully understanding the strong nuclear force that binds literally everything in the standard model together. It's truly mind-blowing to think about what's happening right now beneath the Swiss-French border. By hunting down a ridiculously low-energy photon and finding an excited composite particle, humanity has peeled back yet another layer of reality itself. So with the strong nuclear force slowly but surely revealing its deepest secrets to the Atlas team, I want to leave you with this to ponder. What fundamental, reality-bending mysteries of the universe will the Large Hadron Collider crack next? Thanks so much for joining me on this explainer, and keep your curiosity hungry.